Hi, these when you're gonna use this notebook, um, first obviously you're gonna have to install locally, as this does not run in it will not run in Google Cloud Colab. So you have to install all the dependencies locally from the main GitHub um, repository, and basically um, the the only really change or thing that you have to input here is going to be a image from your local path. Um, I did this in case that you have to work with children's handwriting, and due to regulations and restrictions that we have with that, I uh, I err on the side of caution and actually did the code so the original image, will be input locally. We usually have to change that. It's just this line of code right here. Um, I'm sorry, this line of code right here, which I'm taking a sample image or a original image, and I'm bringing that image, I'm referencing that image on my code. So basically here, um, I created a variable for a for my local machine, and the uh, .env or um, the environmental file, where I reference my local drive. It would be different for yours, and then obviously you gotta have to give it a sample image. Just in case, I will provide this image as well in the repo. So in case you want to use it, the same image, you can. Um, but again, in case that you're gonna use image from children and their handwriting, remember it has to be stored locally. Um, Besides that, the code runs from top to bottom. And so let me go through the steps. First, uh, I just wanted to visually see the image that I'm bringing in, the text that I'm bringing in. Um, so this is something that I hand wrote myself. And basically, I'm just outputting the image so I can see it in the notebook, and kind of give it a visual inspection. Then this piece of code right here is from a library called de-skew, which you have to download again as a separate repo in your local machine and um, reference it in this notebook. If we go right here, um, this part right here is where I do that. So basically, this repo is sitting in a directory separate from the main repo because it's not part of the Story Squad repo. And I saved it in a local path, and I'm just referencing the the path here, and then this is the where the main repo uh, for de-skewing lives. This was the one that gave me the best results, including de-skewing. This included an OpenCV. I found this the easiest and the one that gave me the best results. It gives the best results on images, on full images, meaning it doesn't do that well in line. Like if you segment or do pagination on lines, of text and then try to deskew it, I got some horrendous results with that. Uh, I think it works best if you deskew first and do the segmentation, the pagination after. So just a word of warning on that. I didn't get good results otherwise. But anyway, all I'm doing here is, like I said, I'm referencing the path to that repo that is outside um, to that secondary repo because the that repo doesn't have a pip installed, so you had to manually reference it as you would um, any other Python file. So from here, I'm from this queue, I'm importing determine SQ. And basically what the what the repo does is uh, you bring the image in. It has to be grayscale first. I'm sorry. First, you have to pass it through iSky image, and the function is IO. I have some issues with the default IO from Python, so I rename it IO Sky to differentiate between this IO and this IO. But besides that, you're reading the image, which converts it into a array. Then um, um, is reading the image. Then you graying the image. Then you changing the angle. You determine the angle or the when you grayscale it, you determine the skew that the image has. In this case, as you can see, the image here is slanted on a skew, on an angle. And what we want is go straight. So if you want, you see this line, I want that line to be horizontal, correct? Not in an angle. So the library determines the library determines, okay, the function determines, I'm sorry, what the skew is, and then once it got the skew, then it rotates the image using that angle right here. And as you can see, it rotated this particular image about 10 degrees, right? So if you see the image now de-skew, you can see that the line on the page runs horizontal to my screen, not at an angle anymore. So this really helps, as you can, as I will show you later on, and Tesseract being able to extract the text correctly. So I so once this is done, um, we do the pre-processing. As I said, I found the skewing the complete page first is better, and then I pre-process the image um, because this image is really big. As you can see, is 4,000 pixels by 3,000, which is a huge image. I resize that, and here I'm passing the percentage. So I'm resizing 30% on the x-axis, on the y-axis. Then just to make sure in case the image is not RGB, which is needed by Tesseract, I'm making sure this is, if it's BGR, it becomes RGB. Then I'm taking that RGB image and I'm converting to grayscale. And then I'm using this function the OpenCV has. It's called adaptive threshold. Um, and basically here, what we're doing is to remove the background. And you see where it says trash binary? These two numbers are the ones that you can play with to adjust how much noise and how much contrast do you have. The more contrast you have, normally the more noise you get on the image. So if you change those two numbers, you will see the different results that you will get. I will try to do a couple images with different results so you guys can see it. Uh, I created a function here uh, to do the to de-skewing, so I can then include that as a helper function, but I kind of run out of time and couldn't implement that. But basically, this is this code right here, which, like I said, I want to create a helper function within the pre-processing function at some point. Then here, I'm just creating, I'm outputting an image. So this is the image. Once the image get de-skewed, um, here in this line, I'm putting the de-skew image. So if we look at just the de-skew image, which I showed before, don't worry about this. You will see then the pre-processing that is going to become, the black is going to become white. So don't worry about these black sections here of the image. Well, going back, so going back to the code, like I said, here I'm just running my function, which is the pre-process image, which I showed before, and I'm passing the de-skewed image that I just showed you, and then I'm just um, uh, um, outputting that image, and I'm calling output process PNG. So the de-skewing produces or outputs the output de-skew PNG image, and then once it gets pre-processed, it goes to a function of pre-processing is on those steps. It outputs the um, output process image. So this is the finalized image after the pre-processing is done. And here's how the image looks. Like you can see, a lot of the lines are gone in between the text. This helps the OCR actually read the image better. And like I said, everything that was dark out here became white because it's a transparency really. So um, the PNG actually files carry transparency, so it wasn't really black, it was just transparent. So the same thing here, it's not really white, it's just transparent. You're seeing the white on the background. But as you can see, there's a lot more contrast in the letters. Like I said, if I play with the thresholds, I can make it more contrasty, the image, but I will get a lot more noise. So I want to keep my noise down. So you see these right here. If I zoom in, I want to avoid like these things here. Um, so I want to be careful what I do with my threshold. So we get back to the code. So now we output it. We have two images, the de-skew image and the process image. And I like to keep them both because then that will later on will help me when I'm doing my hypothesis testing of the different images. And I'm gonna go through that in a minute. But once I have those two images, I created, I typed the ground truth of that image, of the original image that you have, was actually the actual text that was that is represented in that image, and is the actual text that you want to extract from that image. So we call that, or is it called the ground truth? And so if you go back here, you read the image, delicious substitute for tuna, and your favorite recipes, perfect for creative hors d'oeuvres and snacks, great as a salad topper. So basically, that's my ground truth, and that's the string here. Is my ground truth, and that's gonna be used for my hypothesis testing. And then we are doing three tests. One is the character error rate, the word error rate, and then something that is called something that is called the Levenstein distance. And information theory and linguistics and computer science. This was this Russian mathematician that came out with a metric that you can measure the difference between two sequences, um, in this case of text or strings, and you you can uh, depending on the amount of deletions or changes or insertions that you can make to one string to make it look like, in this case, a ground truth, you can calculate the distance or how much changes would it would take to be like the one string to be like the ground truth. It's a little complex in theory, but at the end of the day, you're gonna get a rating from 0 to 100. And 0 means the text or the string that you're passing is nothing like the ground truth, and no amount of changes basically that you would do will get you to the ground truth, or even close, because basically the amount of deletions, insertions, and subtractions that you had to do are too many. You have to basically change the complete string to make it look like the other string. Now, if you get a score of 100, that means the two strings are the same. No changes are needed because they are identical. But if you get like 90% or 90 rate distance, it means that it would take some doing, but not too much to make the two texts similar. So uh, uh, hopefully I explained that correctly. If not, I'm gonna leave a reference to what the Levenstein distance is. Um, but basically it's a rating between 0 and 100, and for all intents and purposes here, the closest you are to 100, the higher the number, the better. Max 100, the lower the number, 0 is worse. So you want to be close to 100 compared to 0 for this rating. The other two um, work the opposite way. The lower the number, so the character error rate, you want it closer to 0 as possible, similar to the word error rate. So if it's 0, it means all the characters are extracted um, with 100% accuracy, according to the ground truth. And the word error rate is similar, like all the words are extracted as is in the ground truth when you use the OCR. So uh, one, you want to be close to 100. The other two, the first two, the CER and the WER, you want to be close to 0. So taking that into consideration, and now that we understand what CER, WER, and the Levenstein distance rating is, which I just call here rate, um, basically it will give us three numbers. And so the first hypothesis is I just gonna pass the image, no pre-processing, no de-skewing, no anything. And I'm just gonna pass that image directly to the Tesseract OCR using Tesseract, which is a Python wrapper uh, around the binary. It's a Python wrapper for the Tesseract OCR binary. Um, and basically, here, PyTesseract I pass the image and I pass the function that I want image to string. So I'm gonna take the image and try to extract a string out of it. And so my error rate is 100. My word error rate is 100. So it means I didn't get any character that looks like any character that's in my ground truth. And I didn't get any word either. Obviously, if you don't get characters, normally your word error rate is going to be always worse than your character error rate. And my Levenstein distance is 0 because no amount of changes, deletions, or insertions would help me get to the ground truth strings that I have with text. So that's my first hypothesis. So basically, uh, you know, um, null hypothesis state that that both things should be equal. It doesn't matter that I do anything to it, I will get good results. I proved uh, I, I I I disproved the null hypothesis, and basically now I have to make some changes in order for the OCR to be able to 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 extract meaningful text or string from the image that I have. So I run a second hypothesis, in this case hypothesis one, and is uh, again Tesseract out of the box, but this time I'm going to de-skew the image and I'm going to make it and I'm going to give it a grayscale. So I have to give it a grayscale if I want to de-skew. It's just kind of I'm forced to gray it. So and de-skew it. And right away I can see that I got some benefits from just de-skewing the image. So I can see my character error rate improve. It's not what I want. It's still 46. Remember, it's between 0 and 100. So it got half, less than half of the characters are erroneous or are wrong. So a little more than half characters were extracted correctly from the text. Uh, and actually my word error rate is higher than 100, and this happens with the word error rate because actually, like I said, this is extracting this as a word, and there's no such word in my ground truth. If we go back to the ground truth, obviously this thing that is extracting as a word, there's no such word like that here. So actually the extraction made up some words, the LSTM trying to create words out of the image actually created some words that actually are nowhere at all in the English language, but they are definitely not in my grown truth. And that's why we get a score, a rating more than 100, because the word error rate is higher than the amount of words that I have. Now, my Livingston distance rate improved by quite a lot. Here was 0, now I'm getting 56. So there are some changes that I can make to this text and insertions and deletions to make it look like more like my ground truth. That's what this is telling me, this rating here. Now we go to another hypothesis. What about if I uh, use Tesseract out of the box, meaning I'm not going to patch a customized English data, a trained data file? What happens then? But this time I'm not going to do no de-skewing, so I'm going to leave the letters slanted as they were in the original image that we can see here. So I'm going to leave this slanted like that, but I'm going to pre-process the image. So I'm going to leave the text in an angle or incorrectly rotated, but I'm going to pre-process. And I do get some benefit from the pre-processing without the de-skewing, but like you can say, my word error rate is is better. At least it got to 100, so it's not creating words, uh, but it's really not. uh, and it's not returning any words that are actually in the ground truth, but at least it's not creating extra words, um, or not more extra words that are in the actual text. And my character error rate really went up to 76. So that's a 30-point difference in my rating. So this got worse, and also my Livingston distance rate got worse as well, because we went down to 27. Remember, we want the number close to 100 as possible. So my hypothesis with just the de-skewing, I get some improvement, but my word error rate shuts up, and with just the pre-processing, uh, uh, some ratings uh, improve, but it's still not what I'm looking for. So obviously the next hypothesis is, well, what about if I deskew the image and pre-process and take it to pre-processing steps? What happens? Do I get any improvement on my data extraction? And uh, like I suspected and hope, yes, we do. Like you can see, my character error rate, or the character error rate from the process and disk image is really it went down a lot to 19. Um, my word error rate is not where I want it, but it now at least is understanding some words. It's not understanding 66% of the words, but it's understanding roughly 34% of the words that is passing. So there's some improvement now. Like I said, we can see the word delicious here now. We can extract that. Four uh, is the extracted favorite. In your favorite, that's almost a sentence, close to. And creative, the word creative gets extracted. Hors d'oeuvres, I'm getting closer. Gotta say, it's closer than what I would guess as a human. I didn't know how to spell that word when all this started, and I still don't. Um, and topper, so there's some great. So there's a lot of words that now, because of the pre-processing and because of the de-skewing, the OCR is able to extract. Now, the other questions that you're going to have and you're going to probably encounter as well, what about if we train Tesseract and we do a train data set for Tesseract with handwriting? That's a great idea. Previous cohorts uh, have have worked at it, and there's other cohorts that are working at it right now. But it takes an immense amount of data for what I was able to find out to actually get it to a point where it really gives you significant payoff to have a custom data set. So here, actually, by Tesseract, I'm passing this parameter here, this language parameter. And what I'm saying is to Tesseract and Tesseract is use this custom train train file, um, you know, this uh, English train data, um, customized, and this is from the Story Squad Tesseract team that has created this file, and it's similar to a pickle file. Uh, it's eng dot or in this case ssq dot train data, and basically we're using this to pass like custom train data to the handwritten data to the model, to the Tesseract model, and see the LSTM embedded in Tesseract can use that now train data to generalized out of, handwritten that he hasn't seen before, that the model hasn't seen before. And so here, like you can see, that really didn't help. Actually, my scores got worse. This score went up by almost 20 points. This went down by 3, not as bad. And this three, so you can see here, delicious now has a W at the beginning. I still got 4. Favorite was lost. N became M with an M instead of an N. Uh, Great, I still preserve it. And topper, I lost that word. So you can see even visually that I lost a lot of words that I was able to extract before without using the custom trained data. So at this stage, actually out of the box, non-trained and handwriting trained the English trained data set that comes already with Tesseract is better than the custom story squad so far as of June 20th, 2021. So, but as this improve, you might see some improvements in these ratings. But right now, um, I wouldn't use this language data set because it's not helping my scores. So again, we did all of this to compare it to Google Vision and see how Google Vision fares out compared to Tesseract. But before we do that, I just want to, I did a test and I kind of cheated. So we know as a trained data scientist, we're not supposed to pass a trained data to a model to give us an answer because basically we're already giving the model the answer. But I did do that. And the reason I did that is just to see if I just to see if Tesseract could extract an image, um, could extract text, and do it at the rates that we want, the character error rate, the word error rate, and the Livingston distance rate, if it could give us good results. And actually, so basically, I created a I train I created a custom train model based on my handwriting, and these are capital letters on my handwriting, and I actually passed that image to Tesseract um, to actually OCR and extract the text. And I basically, if you see here, the way I did is I have a space, then the B, C, D, E letters, a space, and then these are all kind of bunched up together. So Tesseract, actually, this would be my ground truth, A, B, C, D, E, and this. So basically it would be like if it were 3 words, one has all these letters, the other one has these letters, and the other one also have one single letter. And so I passed that trained image, that image that I used to train Tesseract with. I passed that image. I cheated, uh, and I passed the image, and I said, okay, uh, can you extract anything from this image that I'm passing that you know? And actually, yes, it gave me back this text. This is what Tesseract outputted exactly as my ground truth. So basically has no character errors, no no word errors, and the Livingston distance is 97. So basically, in this case, um, basically, again, this is just to see even if we train data, Tesseract can give me good, can give me some results. So basically, this hypothesis is if I train Tesseract and I use it with trained data, it can recognize the data, the LSTM system. Uh, I know a lot of you are saying, of course, but again, this is just to see if Tesseract will be capable. If I give it all the handwriting in the world, can Tesseract at some point return return a string that is valid? And yes, it can. So moving right along. So like I said, the whole purpose for this was to compare Google Vision with Tesseract and see what each one gave me back. So I use Google Vision. This code is related to Google Vision, and I'm basically bringing in, reading in the image, passing it to Vision types image, which is a function of Google Vision, and in doing Google Vision is doing the text detection here in this line, and basically it's returning to me a string, which I call hypothesis 5. And this is basically the same thing that I gave to Tesseract, but now I'm passing that image skew and pre-process to uh, to Google Vision, and as you can see, it's getting really good scores compared to Tesseract. The best we could do with Tesseract was 19, 66, and 74. With this, we can do 16, 14, and 88. And I actually did another hypothesis, and I said, well, okay, what about if I don't do pre-processing, because I really don't know what Google Vision is doing in the background. That wasn't one of our tasks. I'm just using Google Vision as a base for the scores. I really didn't, it wasn't our task to understand Google Vision, how it works, and the underpinnings. So I said, okay, I'm not going to pass a pre-processed image. I'm just going to pass the de-skew image. So it's just going to make sure that the image is straight, nothing else. And actually, it did even better when I took the pre-processing. So apparently the pre-processing that actually helps Tesseract wasn't help Google Vision at all in their model. So here my character error rate is less than 0. My word error rate is around 5, and my again the Livingston distance rate is 95. So with really little changes, insertions, or deletions, I can mark this text that Google Vision gave me extracted pretty close to ground truth. And basically, if we look at the words here, the only word that I see that is wrong is this one. This is supposed to say tuna, T-U-N-A, and came back as tuni, T-U-N-E. And obviously, that's wrong. But even a word like uh, hors d'oeuvres that a human have a hard time spelling, it actually extracted it correctly. And even the way that I kind of write, where when I handwrite, I sometimes use capital letters in some words, and even got that correctly, like snacks, that's capitalized. Um, and so it did a great job. So in conclusion, this is Tesseract, and here are the results from Tesseract. The best that, sorry, here is Tesseract and the base that we can do with them, with Tesseract. So, in conclusion, Tesseract is not there. Uh, can we improve our pre-processing and get even better results out of the box? Probably. Some more testing have to be done in that end. And definitely, if we had a trained data set with handwriting that we can use, can we improve it? Probably. Um, but I'm going to share with you guys in the notes some testing that other people did and the results that they got also with CER. Um, I don't know if they used it. Some ratings that they came up, which they got Tesseract a little bit closer, but it was like I think with 3,500 written and handwritten samples that they actually trained Tesseract with, and they actually got Tesseract to have better performance, but definitely to get to the Google level, a lot of work has to be done on the training side to get to those numbers that we're getting from Google Vision. I hope this helped, and thank you.